Well, hello again and welcome to our journey into algebra and number theory. This particular section is probably the hardest of the lot. You might care to skip it and just go to the main result, but I'm going to, just for the sake of completeness, go through the various proofs leading up to our main result. And the main result is trying to answer this question of when is this UN group cyclic. We finished last time with a little summary of the structure of the Zn and the UN, and one of the things we've seen is that the U groups are not necessarily cyclic, and the question is when are they cyclic, and I mentioned that one partial answer is when n is prime. So what we're going to prove now is that if n is prime, then the U group is cyclic. Now the converse is false, as we'll see, but that's where we're going to be going. Now to do that we need a number of technical lemmas or lemmata, which we're going to go through and then do a proof of the main result. So the first one is about group theory. So we've got G as an abelian group, and we've got two subgroups A and B of G, such that G is isomorphic to a direct product. So we're going to think of this multiplicatively. So if A and B are themselves both cyclic groups, and the GCD of the number of elements in A and the number of elements in B is 1, then G itself is a cyclic group. This is a result from group theory. By the way, the converse of this is also true, but we don't need that result here. So if A and B are both cyclic, then we're going to let A and B be the generators of capital A and capital B respectively. So we're assuming A and B are cyclic, and we're assuming that the GCD of the number of elements is 1. Then I'm going to put this little g to be the product of these two generators, because this, if A generates capital A and B generates capital B, then the obvious choice for a generator for the group G is to take their product. Now the orders of A and B are relatively prime, and that means the order of, so G has order, size of A times the size of B, which of course is just the size of G. That means if I take all the powers of G, little g, I'm going to get exactly capital G. So G is thus cyclic. The second lemma is about polynomials in ZP. So if we take f of x to be a polynomial of degree n with coefficients in ZP with p prime, then I claim that the number of solutions of f of x is 0 mod p is at most n. Now that's not true if n is not prime. You can find equations which have got a lot more than n polynomials of a certain degree which have more roots than the degree, but if we were in a prime group here, then n is the maximum number of solutions of this, where n is the degree of the polynomial. So firstly we observe that x to the fourth is 1 mod 5 has got 4 solutions, which you should see it follows immediately from Fermat's little theorem, because you can put any number here, 1, 2, 3, or 4 in here, and that'll satisfy it. So in general, f of x can have as many as n solutions, but we're going to prove here it can't have any more than n, provided this number's prime. So we now proceed by induction on n. So if n is 1, then we just have this simple polynomial of degree 1, and a is not 0, mod p, and this obviously has one solution because a and p are relatively prime, so you can multiply the inverse, both sides by the inverse of a mod p, and you'll get x is 0 mod p, and that's the reason why. So now assume the proposition is true for all polynomials of degree less than m, and we now consider, this is strictly less than m, and we now consider the polynomial of degree m. So I'm going to be using sort of strong induction here. I'm assuming it's true for all polynomials of degree strictly less than m, and look at a polynomial of degree m. If it's got no solutions, then, well, we're finished, because then that's less or equal to the degree of the polynomial. If not, then, suppose that x equals x naught is a solution. Now, by the factor theorem, then we can factor out x minus x naught is a factor. And here I'm assuming the basic properties of polynomials carry across to the field ZP, which they do. So I can take this f of x here and I can factor it into x minus x naught times a polynomial degree m minus 1, congruent to 0 mod p. And by assumption, this one has at most m minus 1 roots. And then f of x has those roots plus this one, and so f of x has at most m roots. And so the result now follows by induction. The third lemma, probably perhaps the hardest of them, is if n is a factor of p minus 1 mod of p prime, then x to the n is congruent to 1 mod p, has exactly n solutions. That is, modulo p, there are exactly n roots of unity. X to the n congruent to 1 mod p has exactly n solutions. And the proof of this is a little bit more clever and a bit harder to see the motivation for this, but it's a fairly clever proof. So we know that x to the n congruent to 1 mod p has at most n solutions. We just proved that a minute ago. And we know that x to the p minus 1 mod p has exactly p minus 1 solutions. And why? Well, that's Fermat's little theorem again. Any number x in Zp star will satisfy this equation. So there are exactly p minus 1 of those. Now, since n is a factor of p minus 1, that was our assumption, then p minus 1 is some multiple of n for some integer e. And so I can take x to the p minus 1 minus 1, that's this coming motivated from here. I can then write that as x to the n e minus 1, which is x to the n to the e minus 1. And now I can factorise this. This is a standard factorisation. It's x to the n minus 1 times this polynomial. It's just our standard factorisation of x to the k minus 1. I write this as x to the n minus 1 times f of x, where f of x is now a polynomial of degree n times e minus 1. So we let alpha be the number of solutions of x to the n congruent to 1 mod p, and we know that alpha is less or equal to n by our previous lemma. Now f of x, this polynomial, also has at most that many solutions, and if I go back and replace ne with p minus 1 from here, I get p minus 1 minus n solutions. So that means alpha has to be at least p minus 1, and that says p minus 1 then is less or equal to alpha plus p minus 1 minus n. And that, if you rearrange that equation, we get alpha then is bigger or equal to n. So the fact that alpha is less or equal to n and bigger or equal to n means alpha is equal to n. So that has exactly n solutions. Finally, we come to our main theorem, and if you skip the earlier lemmas, this is the main point here, and that is if p is prime, then up is cyclic. And the proof of this again is slightly difficult. So we're going to write, we take our p minus 1 and we prime factorise it, where the qi's are prime, and that's our prime factorisation of p minus 1. Now what I want to do is, to show this as cyclic, I want to find cyclic groups B1 up to BR of order Q1 to the alpha 1 up to QR to the alpha R respectively, so that this U group is isomorphic to this direct product. I can then apply lemma 1 that says that if these are all cyclic groups and they're pairwise co-prime in size, which there will be from here, then this is cyclic. So to do this, for each of, we need to find for each I a generator for each of these b's. So we need to find an element bi in up of order qi to the alpha I, and then I'm simply going to put bi to be the group generated by this bi. Now for ease of notation, I'm going to write q sub I is q and alpha sub I is alpha. So the argument will work on each of the different subgroups here. So we begin by consider the equation x to the q to the alpha minus 1 is naught not p. Now by lemma 3, this has q to the alpha solutions, but the problem at the moment is there's no guarantee as yet that any of these numbers has order q to the alpha. It certainly may be true that x to the q to the alpha minus 1 is 0 mod p, but we don't know that this is the smallest power that makes this true. Now x to the q to the alpha minus 1 mod p has, by our lemma, q to the alpha minus 1 solutions. So that means there are q to the alpha minus q to the alpha minus 1 values of r, values of x I should say, which satisfy the first of the above equations. That is this one, but not the second. So these numbers must have order q to the alpha. So we can pick any of those, and that will generate our group bi, and so that means this group is cyclic. That means that u sub p is direct product of these cyclic groups, and that will also be cyclic. Moreover, we actually can get a formula now for this, because there were that many generators for B1, that many generators for B2, and so on. And if you look at this, this is simply phi, because our p minus 1 was up here. This is simply phi of p minus 1. So that gets me a nice result as well, that there are phi of p minus 1 generators. And we're going to look at these in more detail in a second. In fact, we're going to give these a special name. We're going to call these primitive roots. So a generator of u sub n is going to be called a primitive root modulo m, or PR for short. If m is prime, then there are phi of m minus 1 such primitive roots, and these play a very important role in number theory, as we'll see later. So again, we're seeing this nice interplay between the algebra and the number theory. Now, it's easy to see that u2 and u4, because they're very simple, have primitive elements. This just consists of element 1, and this just consists of 1 and 3, so 3 is a generator. So these have primitive roots. And observe that if p is an odd prime, then we can take u2p, and I can factor it as u2 cross up, and u2 is just 1, so this is just isomorphic back to up, so that says u2p is also cyclic. Now for the full story, it's also possible, but more difficult, and I'm not going to do that here, to prove that p to the k is cyclic, and hence by the same argument up here, u2p to the k is cyclic as well. And more importantly, that's the end of the story. There are no more. In other words, I summarise this in our theorem 8. Um is cyclic if and only if, this is a lovely, lovely theorem, if and only if m is 2 or 4, that's a bit of noise, a power of a prime or twice the power of a prime, where p is an odd prime. This doesn't work for p equals 2, by the way, and k bigger or equal to 1 as an integer. So that's the full Monty, that's the full result on when this group is cyclic. Now, just as an example here then, I want to find a primitive root modulo 62. 62 is twice 31. So as we've seen before, u62 is isomorphic to u31. So we're going to find a primitive root mod 31. And that will also work for the primitive, as a primitive root modulo 62. So thus what we need to do is we need to find an element of order 30, because 30 is 562. So I'll leave you to check, which is easy to see because this is twice 31. Now 30 is 2b3b5. So we need to find a number a, so that a to the 15, we get that from taking 30 divided by 2, a to the 10, that's 30 divided by 3, and a to the 6, that's 30 divided by 5, but none of those is 1 modulo 31. Well, where do you start? Well, you start at 2. Start at the beginning, we try a is 2. However, 2 to the 5th happens to be 1 modulo 31, and so that's the end of that, because then 2 to the 10th is 1, and so it doesn't have the right order. Okay, so 2 failed. Back to the drawing board. What do you do now? Well, you try the next number. Try 3. So I just did some calculations. 3 cubed turns out to be -4. 3 to the 10 comes out to be 25. So that's nice. 25 is not 1. 3 to the 15 turns out to be -1 mod 31. Again, that's good. That's not 1. And from this one here, we can see 3 to the 6 is going to be 16, which again is not 1. So that tells me 3 is a primitive root mod 30, and hence a primitive root mod 62, and that means U62 is generated by 3. So it is a cyclic group. As expected, it's twice a prime, and it's got a generator, and there it is. Now we'll look a bit more in a moment in the next video to see how to actually get these primitive roots. We need a few little more results to make getting this a bit easier. So little exercise you might like to do is to show that phi of 385 is the same as phi of 610, but then to show that these groups are not isomorphic. The point here being that you can have phi of m equals phi of n, but the two groups, un and um, are not necessarily isomorphic. In the next video, we're going to have a look at results, useful results for determining, to help us to determine primitive roots, and we'll also look at some applications of these to solving various congruence equations.